In the beginning, there was no beginning. No ticking clocks, no unfolding seconds, no before or after. There was only silence, an emptiness so profound it defies the human mind. And then, in a fraction of a moment, the silence was broken. Out of nothing, the universe ignited. Energy, matter, and the fabric of reality itself surged outward in an instant we call the Big Bang. It was here, not in space, but with space itself, that time was born. Einstein's theory of relativity had already whispered this truth, that space and time are not separate, but woven together, inseparable threads of a single cosmic fabric. To move through space is to move through time. To bend matter is to bend both. And so, when space unfurled, so too did time's first trembling heartbeat. Yet this birth carries a paradox. If time began with the Big Bang, then what lay before? Can there be a before, when the very concept of before depends on time already existing? It is here that science brushes against philosophy, and reason stumbles into silence. Stephen Hawking once proposed an answer, the no-boundary condition. In this vision, the universe has no sharp edge, no singular beginning, no line where time simply starts. Like the surface of a sphere, it curves smoothly upon itself. There is no before the Big Bang, just as there is no edge to Earth's horizon. And yet, as humanity stares back toward that first instant, one question lingers with haunting persistence. If time itself was born in that blinding eruption, what mystery lies behind a curtain that cannot, by definition, be pulled aside? Time does not merely pass. It drifts in a single, relentless direction, dragging all things with it. A shattered glass does not leap back together. A candle's smoke does not return to its flame. A body that has aged does not grow younger. This one-way motion, so ordinary in daily experience, is in fact one of the greatest paradoxes in science. For in the deep mathematics of the universe, time is not required to flow forward. The laws of physics, the equations of Newton, of Maxwell, of Schrödinger, are symmetrical. They do not care whether time runs from past to future, or from future to past. If a particle can move left today, it can move right tomorrow. If two atoms can collide in one direction, the same laws would allow them to uncollide, retracing their every motion. At the most fundamental level, the universe does not appear to favor forwardness. And yet, the human world does. Tea poured into a cup grows cooler, but never hotter on its own. Smoke disperses, but never regathers. Ice melts into water, but water does not freeze without reason. This is the arrow of time, the inescapable directionality of reality. It is not written in the equations of quantum mechanics or relativity. It is written in the rise of entropy. Entropy is the measure of disorder. A deck of cards perfectly arranged is low in entropy. Shuffle it, and the disorder increases. The second law of thermodynamics tells us that entropy, in a closed system, always tends to increase. And this increase creates the sense of irreversible time. A glass that shatters into shards increases entropy. Disorder grows. For it to reassemble, entropy would need to fall, improbably, against the weight of statistical chance. Ludwig Boltzmann, the Austrian physicist of the 19th century, sought to explain this. He imagined a gas in a box, its atoms darting randomly. The more ways the particles could be arranged, the greater the entropy. And since disorder vastly outnumbers order, systems naturally evolve toward higher entropy states. In this view, The arrow of time is nothing more than probability. It is simply more likely for things to grow disordered than to return to order. But Boltzmann's answer, though elegant, carries its own haunting riddle. If the laws of physics are symmetric, if they do not distinguish forward from backward, why did the universe begin in such a low entropy state to begin with? Why was everything ordered enough to allow entropy to increase at all? Consider the earliest instant of the cosmos. The Big Bang produced a universe filled with blazing heat and uniform density. To the human mind, this seems chaotic. Yet in terms of entropy, it was extraordinarily ordered. For gravity had not yet had the chance to clump matter into stars, galaxies, and black holes, the true engines of disorder. The universe began with astonishing simplicity, a condition of improbably low entropy. And from this improbable beginning, time's arrow was set. Every increase since, the collapse of stars, the burning of suns, the spreading of light, has been an unfolding of that original imbalance. Boltzmann himself wondered whether this low entropy origin might be only a local fluctuation, a chance alignment in an eternal cosmos. Perhaps, he speculated, the universe spends most of its existence in timeless equilibrium, but sometimes, improbably, order emerges, and from it, a temporary arrow of time. But this suggestion raised an unsettling implication. If the cosmos is eternal, and time is infinite, then what we see as the universe may not be typical at all. Instead, far more likely would be a single brain, assembled by chance fluctuations out of chaos, a Boltzmann brain, experiencing the illusion of reality. The very fact that we see an ordered universe full of galaxies, stars, and life suggests something deeper than chance. Something about the birth of the cosmos preferred low entropy. Something set the arrow in place. The problem grows darker still. Imagine rewinding time. Every star that collapses becomes a gas cloud once more. Every broken glass reassembles. Every life is lived in reverse. Nothing in the equations of relativity forbids it. Nothing in the mathematics of quantum mechanics rejects it. But in our universe, it does not happen. Why? The arrow of time, then, is not a law of physics, but a law of boundary conditions. It is not the rules that drive time forward, but the starting point itself. A beginning that was low in entropy makes forward flow inevitable. Time is the story of entropy unfolding from an unlikely first moment. And yet, this explanation only deepens the paradox. For why should the universe begin in such an improbable condition? What mechanism set its entropy so low? The Big Bang could have been a chaotic explosion of maximum disorder, yet it was not. It was balanced on a knife's edge of simplicity. Modern cosmologists wrestle with this. Some suggest cosmic inflation, the exponential expansion in the earliest fraction of a second, may have smoothed the universe into its ordered initial state. Others suggest that universes may come in pairs, one with time flowing forward, another with time flowing backward, each beginning in low entropy but in opposite directions. In such a vision, our arrow is not unique but mirrored, branching away from a common origin. Still others believe the arrow itself may be an illusion of perception. Perhaps entropy increases only because consciousness orders events into a sequence. Perhaps the universe itself is timeless, a block where past, present, and future coexist, and what humans call the flow of time is nothing more than the movement of awareness along that frozen landscape. Yet entropy remains stubborn. Every burning star, every crumbling mountain, every decaying atom is evidence that disorder grows and grows irreversibly. The arrow of time is everywhere, though its origin lies in mystery. It is the paradox that shapes human life. Without entropy, there is no memory, no cause leading to effect, no distinction between before and after. The arrow of time is therefore not only a puzzle for physics, but the foundation of existence itself. It explains why lives move forward, why histories are written, why death is final. And yet, deep in the mathematics of the universe, no such arrow is required. The universe may not care for forwardness. Its laws may allow a river of time flowing equally well in either direction. And if so, then the human arrow, the relentless march into the future, is not a necessity of physics, but a consequence of an improbable beginning, a seed of order from which disorder must always grow. This seed, this impossible simplicity, remains the most enduring mystery. Why did the cosmos start so improbably pure? Why was entropy set so low against the weight of all probability? Science offers no final answer, only the haunting recognition that in that origin, the fate of time itself was written. And so the arrow endures, fragile, unexplained, and absolute. The tea will always cool, the smoke will always disperse, the glass will always shatter. And behind each simple act of irreversibility hides the greatest question of all. If time's arrow need not exist, why does it exist at all? For most of human history, time was not a mystery. It was a given. The sun rose, shadows moved, the seasons returned. Time was the silent backdrop against which existence played out. It flowed forward with unbroken certainty. But when the first great equations of nature were written, they revealed something unsettling, something that contradicted the everyday experience of irreversibility. In the mathematics of the universe, time could just as easily run backward. Isaac Newton's mechanics were the first glimpse into this hidden symmetry. His laws of motion, formulated in the 17th century, were astonishing in their clarity. They described a clockwork cosmos, where every planet, every falling apple, every grain of dust obeyed the same precise rules. But within Newton's equations lurked a strange revelation. If one could take the positions and velocities of every object in the universe and reverse them in perfect detail, the equations would still work. A falling apple could rise back into a tree. A pendulum swing could move from rest to motion without a push. The laws did not care about direction. For Newton's cosmos, time was not an arrow, it was a mirror, indifferent to past or future. This symmetry grew even more profound in the 19th century with James Clerk Maxwell. Maxwell's equations of electromagnetism united light, electricity, and magnetism into a single elegant framework. They revealed light itself as a wave traveling through space-time, yet these equations too were ambivalent about the flow of time. A beam of light could radiate outward from a star or converge inward into it. The equations made no distinction. To Maxwell's mathematics, the past and the future were equally valid solutions. And so, the symmetry deepened. With Newton and Maxwell, humanity discovered that nature's most fundamental rules did not insist on forwardness. They admitted a universe where every event could be played in reverse with no violation of physical law. But if this was true, then why did no one see the shattered glass reassemble, or the smoke flow back into a flame? Why did reality itself resist the reversibility its equations allowed? The puzzle sharpened as the 20th century dawned, when a new language of physics emerged, quantum mechanics. In 1926, Erwin Schrödinger proposed his wave equation, a tool to describe the behavior of particles at the smallest scales. It revealed a strange world where matter existed as waves of probability, collapsing into certainty only when observed. Yet once again, the mathematics was symmetric. Schrödinger's equation could run forward or backward with equal legitimacy. It was as if nature had drawn two blueprints, one for forward time and one for reverse, and then chosen only one to inhabit. The shock was not only in the symmetry itself, but in its persistence across the deepest layers of physics. Mechanics, electromagnetism, quantum theory, all pointed to a reality where time's direction was not fixed. Some scientists, like Richard Feynman, would later take this symmetry to its extreme. He proposed that antimatter might be understood as matter moving backward in time. Every electron could, in principle, have a partner racing in reverse through the temporal fabric. What appeared to us as annihilation, the meeting of matter and antimatter, might be nothing more than two paths of time crossing one another. The implications were staggering. If the laws of physics truly allowed reversibility, then the arrow of time, so deeply ingrained in experience, was not fundamental at all. It was emergent, fragile, perhaps even illusory. The universe, at its core, was timeless. The arrow existed only in the macroscopic world where entropy ruled. But in the microscopic language of particles and waves, there was no forward, no backward, only symmetry. And here lies the haunting paradox. The very fabric of existence, written in equations by Newton, Maxwell, and Schrödinger, does not demand that tea cools, or that stars burn out, or that lives move from birth to death. Those certainties belong to the world of entropy, of statistical inevitability, not to the bedrock of physics. In the truest sense, the equations tell us that the river of time could flow either way. This was the discovery shock, the realization that reality's most fundamental grammar does not forbid reversal. It was not the universe that insisted on the arrow, but something else, something hidden in its birth, in its boundary conditions, in the improbable low-entropy state from which all things began. The great irony is this: the deeper science probed, the less it found evidence for time as humans know it. The clock that rules daily life, the ticking of seconds, the irreversible drift toward the future, was not etched into the laws of motion or the equations of light. It was nowhere in the quantum waves of probability. It emerged, somehow, from the improbable way the universe began. And so, the early equations revealed a truth as unsettling as it was beautiful: that time, as experience knows it, is not woven into the mathematics of the universe. It is an arrow that should not exist. In the cathedral of physics, where equations rise like stained glass windows into the vaulted ceiling of human thought, symmetry has always been the guiding light. Symmetry is elegance. Symmetry is truth. From the spin of planets to the dance of quarks, it whispers that the universe, in all its strangeness, may be governed by a deeper order than what meets the eye. Yet among the symmetries of nature, one stands apart. It is neither simple nor intuitive. It is a law that suggests the universe holds a hidden mirror, an echo of existence itself. It is called CPT symmetry. C for charge, P for parity, T for time. 3 letters, 3 reflections, a trinity of balance in the laws of physics. Charge symmetry imagines a world where every particle trades its electric cloak for the opposite. Positive becomes negative, negative becomes positive, and the mathematics of nature remains unchanged. Parity symmetry flips space itself. Left becomes right, right becomes left, as though the cosmos were seen through a mirror of unimaginable scale. And time symmetry T whispers the most haunting possibility of all. Reverse the arrow, let clocks run backward, let effects precede causes, and still the fundamental equations of physics hold their form. Taken alone, each of these symmetries can be broken. Experiments have shown violations, but together, as one indivisible principle, CPT symmetry has never been seen to fail. No matter how reality is twisted, inverted, or reversed, the laws remain valid, as though the universe insists on balance even in its most alien reflections. It was a revelation that unsettled the scientific imagination, because hidden within it lay a suggestion that time, as experienced by every conscious being, may not be as singular as it feels. Richard Feynman, with his chalk-stained hands and restless mind, offered a daring interpretation. To him, antimatter was not merely matter's opposite. It was matter moving backward in time. A positron, with its positive charge, could be seen not as a new kind of particle, but as an electron retracing history, a flicker of existence flowing upstream against the river of entropy. In the halls of physics, this idea was met with both wonder and unease. Could every annihilation, every brief flare of particle and antiparticle meeting be read as 2 travelers on opposite roads of time, colliding in the present? Could antimatter be the evidence of a universe where time is not a one-way street, but a 2-lane highway, with traffic flowing both forward and back? To some, it was poetry disguised as physics. To others, it was a glimpse into the hidden architecture of reality. And yet the unease remained. For if antimatter truly moved backward in time, what did that imply about causality itself? In the ordinary world, the arrow of cause and effect seems absolute. A glass falls, then shatters. A flame burns, then turns to ash. But in this vision, such absolutes blur. Perhaps what we call effect is simply another cause, viewed from the wrong temporal direction. Perhaps reality is a story written to be read both forward and backward, depending only on which end of the script one begins. The equations supported this symmetry with ruthless precision. The Dirac equation, which first predicted antimatter in the 1920s, carries within it the seeds of time reversal. Maxwell's equations of electromagnetism bend but do not break when clocks are run backward. Quantum field theory itself demands that CPT symmetry hold, or else the very foundation of physics collapses. And so, with every experiment, with every collision inside accelerators, the symmetry held. No violation, no exception. Nature, it seemed, demanded this hidden mirror to remain unbroken. But what does it mean, truly, to imagine time reversed? Consider a film of a single hydrogen atom, its lone electron orbiting a proton. Run it backward, and the motion remains indistinguishable. The mathematics cares little for direction. Yet when that atom collides, when entropy enters the story, when disorder begins its ceaseless march, the illusion shatters. Entropy pulls forward. The arrow returns. And here lies the paradox. The laws are symmetric, but the world we inhabit is not. Entropy gives time its sting, its irreversibility. Yet CPT whispers that underneath the chaos, a perfect balance remains, waiting, hidden, unbroken. Philosophers of physics wrestled with this revelation. Was antimatter evidence of another universe? A mirror world flowing backward from our beginning to its end? If one could step into its frame, would death become birth? Would memory become prophecy? Or was it only a mathematical convenience, a reflection without substance, a symmetry existing solely on paper? In laboratories, the search pressed on. Antihydrogen atoms were trapped and cooled, their spectral fingerprints measured with exquisite precision. Each observation confirmed, the mirror holds. No deviation, no flaw. If antimatter is time's shadow, it hides with perfect discipline. And still the question lingers like a riddle, unsolved. Is the flow of time? We know, the relentless push from past to future, only half the truth. Is there, unseen, another current running beneath us, where effects precede causes, where beginnings and endings trade places, in a cosmic symmetry beyond our perception? The shock of CPT symmetry was not simply that the equations allowed reversal. It was the haunting suggestion that our universe may be far stranger than lived experience admits. That in the quiet precision of mathematics lies a truth both terrifying and beautiful. Reality may be fundamentally ambidextrous, moving forward and backward at once, while consciousness clings to only one side. And if that is so, then the great mystery deepens. For what, then, is time itself? Is it a river with one true direction, or is it a mirror, reflecting two truths, forever inseparable, forever unseen? In the silence after the birth of the cosmos, time began its march forward. Or so it seems from the vantage of this universe. From the first tremors of expansion, every particle, every star, every breath of life has followed the same current, swept along the one-way river of time. Entropy increases, memories form, civilizations rise and fall, and the future waits ahead like an endless horizon. Yet deep within the mathematics of cosmology, a startling possibility emerges. The arrow of time might not be unique. Perhaps it does not simply point outward, forward, into what we call the future. Perhaps time, like the great universe itself, could branch, flowing in two directions, away from a common origin. A universe with two arrows of time. A cosmos split not by space, but by the very direction in which events unfold. To imagine such a thing is to stand again at the Big Bang, not as a distant historical moment, but as a timeless surface of origin. The singularity, or what stands in place of one, was not merely a beginning. It was the point of lowest entropy, the most improbable order the universe would ever contain. And from that improbable order, entropy began to rise. Here, on this side, it rose forward, writing the history we inhabit. But in principle, nothing forbids entropy from rising in the opposite temporal direction as well. From that same seed, another universe might unfold, not parallel in space, but in time, moving ever farther into what to us would look like the past. A cosmic mirror, unseen, unreachable, yet bound to us at the deepest level of physical law. This idea has captured the imagination of physicists and philosophers alike, Sean Carroll, a leading voice in modern cosmology, has argued that the arrow of time must be explained not by the laws of physics, since they are time-symmetric, but by the boundary conditions of the universe itself. In Carroll's framework, the low entropy of the Big Bang is not a puzzle to be dismissed, but the very clue that hints at something larger. From that initial state of extraordinary order, the universe need not flow in one temporal direction only. Instead, it could give birth to two branches, two arrows, pointing away from the same origin. One, the cosmos we know; the other, an unseen twin, expanding into what we would call the reverse. In such a model, the Big Bang is not the beginning in any ordinary sense. It is a dividing surface, a cosmic equator of time. The mathematics of statistical mechanics and cosmology makes the thought strangely plausible. Entropy always increases from low to high. The Big Bang was the lowest possible entropy state, then entropy must climb on both sides of it. From our perspective, the universe runs forward. From the other, it runs backward. But to the inhabitants of that opposite branch, their time feels just as natural as ours. They too would see stars forming, galaxies unfolding, life perhaps emerging, yet all along their arrow of time. The implication is haunting. For every memory we carry of the past, their universe would carry memories of what to us seems the future. It is a vision that unsettles the human sense of direction. We are creatures tied to chronology. Our language itself is threaded with temporal metaphors. We look forward, we remember back. Birth is behind us, death ahead. But in this cosmological mirror, the very meaning of ahead is fractured. Could it be that while we live our stories in one temporal flow, there exists another cosmos where stories bloom in reverse, yet not reversed to them? Their hearts would beat forward, their stars would burn forward, their children would be born and grow. To us, it would all look like a film played backward. To them, it would be as seamless as our own unfolding. This is not science fiction. It is the logical outgrowth of time-symmetric laws applied to the greatest mystery of all: why time seems to have a direction at all. The concept of two-way time carries profound philosophical weight. If entropy increases both ways, then what we call the past may not be a singular absolute. It may be simply our side of a broader truth. What we see as the distant past, the Big Bang itself, would not be the universal beginning, but the midpoint of a grander structure, an hourglass with time pouring out in two directions. And yet, if such a twin universe exists, it remains forever out of reach. The two branches, though born of the same seed, expand apart through their own temporal horizons. We cannot step across, cannot communicate, cannot share even the faintest signal, for to do so would require defying the very arrow of time itself. Still, the idea lingers like a reflection glimpsed in a darkened glass. Carroll and others suggest that this two-arrow model may resolve one of the most profound cosmological paradoxes. Why was the universe born in such an improbably ordered state? The chance of such a low entropy beginning, by blind roll of the cosmic dice, is staggeringly small. And yet, we are here. In a two-way model, the low entropy of the Big Bang is not a puzzle demanding an unlikely explanation. It is simply the natural origin point from which entropy must rise in both directions. The improbability is dissolved by the structure of time itself. It is a reminder that the deepest mysteries are not solved by erasing them, but by reframing them. To Feynman, particles of antimatter could be understood as matter moving backward in time. In a similar spirit, to cosmologists, a twin universe flowing backward may be as real as our own, though beyond the veil of reach. If so, then reality is stranger than any myth humanity has ever told. The cosmos would not be a single river of time, but a delta branching in opposite flows from the same source. We on this shore can only speculate. Our instruments measure only our arrow, our expansion, our galaxies drifting farther apart. But the mathematics whispers of the other shore, invisible, carrying its own suns, its own physics, its own unfolding eternity. And so the universe may be a two-way street, a street upon which we travel one direction, but which in another realm is traversed the other way. Each side believing itself to be the forward travelers, never knowing the other exists. The idea leaves us suspended between science and philosophy, between physics and wonder. For if time itself can branch, if universes can unfold with opposite arrows, then the ultimate question remains. Is the universe we see all that is, or merely one half of a grander symmetry? A reflection lost beyond the horizon of time? The answer, if it exists, is written not in the stars, but in the silence between them. In the hidden theater of the quantum world, time itself appears less like an arrow and more like a shimmering mirage. Particles do not march forward with steadfast certainty, nor do they obey the orderly cause and effect that defines the macroscopic realm. Instead, they drift like actors who know the ending before the play begins, weaving stories that seem to fold both forward and backward through the fabric of reality. Here, within the smallest structures of existence, the very flow of time begins to flicker, as though the universe were whispering a riddle that defies all common sense. At the heart of this mystery lies quantum entanglement, a phenomenon so unsettling that Albert Einstein once dismissed it as spooky action at a distance. Two particles, born together, can remain bound across any gulf of space. When one is measured, the other responds instantly, as though some hidden thread ties their fates. But what is more disturbing is not merely their synchrony. It is the implication that the outcome of one measurement seems to decide the reality of the other, even if they are light years apart. In certain interpretations, the correlation is so tight, so absolute, that it almost seems as though one particle's present moment is reaching back through the fabric of time to shape the other's history. Some physicists whisper of retrocausality, the idea that in the quantum domain, causes may flow not only forward into the future, but backward, reshaping the past. Experiments have deepened the unease. In the 1970s, John Wheeler, one of the great visionaries of physics, proposed a thought experiment, the delayed choice experiment. Imagine light streaming from a distant star, traveling across the cosmos for billions of years. That light can be treated as a wave, spreading across multiple paths, or as a particle confined to a single trajectory. According to quantum mechanics, the way it behaves is not decided until it is observed. Now, Wheeler asked, what if the decision of how to observe the light is made only after it has crossed its path? Could the observer's choice today determine whether the photon behaved like a wave or a particle billions of years ago, at the moment it departed its star? In 2007, such experiments were finally realized in laboratories on Earth. The results were as unsettling as Wheeler suspected. Photons appeared to decide their past behavior based on a measurement made in the present. Reality seemed to rewrite itself in accordance with an observation that had not yet occurred when the photon began its journey. This bizarre suggestion found its most haunting form in the delayed choice quantum eraser experiment, first conducted in the 1990s. In this experiment, entangled photons are generated and sent along two different paths. Some of these photons strike a detector that can reveal whether they traveled as waves or as particles. But in certain cases, the experimenter has the power to erase the information, preventing the photon from ever revealing its nature. Here lies the twist. The decision to erase or preserve the data can be made after the photon has already been detected. Yet the results seem to imply that the photon's earlier behavior, wave or particle, depends on the future choice. The future appears to reach back into the past, reshaping it, as though time itself were a canvas still wet with paint, awaiting the final brushstroke. Quantum mechanics, in its standard formulation, avoids outright contradiction by describing such effects in terms of probabilities and wave functions. Nothing, it insists, is truly decided until an observation collapses the possibilities. But the interpretation of these experiments remains deeply contested. Some physicists argue that the photon's past was never fixed until the full chain of events was considered, and thus no retrocausality truly occurs. Others suggest that perhaps all possible histories exist, branching like a vast tree of realities, until an observation selects the path we perceive. Yet lurking within these explanations is an unavoidable unease. The rules that govern the quantum world do not respect the everyday flow of time. They treat past and future not as separate realms, but as interchangeable directions, woven together in equations that are perfectly symmetric. Consider the Schrödinger equation, the core mathematical law of quantum mechanics. It is, like Newton's laws and Maxwell's equations before it, perfectly time-reversible. The equation does not insist that events must progress toward the future. Run backward, it describes a universe that is just as valid, just as possible. And so, when one descends into the quantum, the arrow of time that governs the thermodynamic world above seems to vanish. Heat may dissipate, entropy may rise, but at the deepest levels of particles and waves, the laws remain eerily indifferent to direction. This indifference has fueled radical interpretations. Some physicists propose that particles do not simply exist in the present, but also reach through the corridors of time, influencing both what has been and what will be. In Richard Feynman's formulation of quantum electrodynamics, antimatter itself can be interpreted as ordinary matter traveling backward through time. Every positron, in this view, is not a separate entity, but an electron retracing history in reverse. If true, then perhaps the backward whispers of causality seen in entanglement and delayed choice experiments are not anomalies at all. They may be hints of a deeper symmetry, one that binds the forward and backward directions of time into a single seamless whole. Philosophical unease grows with every revelation. For if observation determines reality, and if observation can rewrite the past, then what does it mean for history itself to be real? Is time merely an emergent illusion, a construct shaped by consciousness sifting through probabilities? Or is the universe itself timeless, with past and future existing side by side, like pages in a book already written, waiting only for perception to reveal their sequence? An experiment conducted in Vienna tested whether information in entangled systems could be influenced across temporal gaps. Entangled photons were measured in ways that suggested correlations persisting, even when one measurement occurred after the other should have been fixed. Again, the results aligned with quantum predictions. Again, they unsettled our deepest intuitions. The data did not allow faster-than-light signaling, nor did they permit communication with the past. Yet the correlations suggested a world where temporal order is not fundamental, but emergent. In this realm, it may not be time that dictates cause and effect. It may be information itself, binding events across the divide we call past and future. And so, the question deepens. If time can bend within the quantum, if the future can shape the past, what does this mean for the arrow of time that dominates human life? One possibility is that time, as experienced, is a statistical illusion. Entropy, ever increasing, builds the stage upon which memory, history, and factor and causation appear to exist. But beneath the surface, at the most fundamental scales, the universe may not move. It may not flow. It may simply be a timeless structure, like a crystal, in which every event, past and future, already resides. Yet this interpretation does not quiet the unease, for it suggests that what is felt as becoming, the birth of stars, the cooling of tea, the rhythm of a heartbeat, is not the universe unfolding, but consciousness tracing a path across a fixed, steep, eternal landscape. The arrow of time may be nothing more than the shadow of entropy, projected onto the stage of perception, and beneath that shadow lies a world where time can just as easily run backward as forward, where the past may be malleable, and where the future is not an open horizon, but an already written page. Still, within the silence of quantum reversals, a profound beauty emerges. For in the uncertainty of particles, in the haunting suggestion of retrocausality, the universe reveals that it is stranger than imagination, deeper than logic, and more mysterious than any myth once told. The story of time may not be the story of an arrow, but of a mirror in which past and future face one another, indistinguishable, reflecting endlessly into a symmetry that is hidden yet eternal. And in that symmetry, perhaps lies the ultimate truth, that time as it is lived is not the measure of reality, but the measure of perception. That causality is not absolute, but conditional, and that the universe, vast and inscrutable, is not bound by the flow of time, only by the dance of possibility. Time, as lived by human beings, feels like a river that flows ever forward. From birth to death, from dawn to dusk, its current carries every moment away, never to return. Yet in the deep mathematics of the universe, equations whisper of something far stranger. They speak not only of streams, but of circles, not only of flow, but of loops. In 1915, Albert Einstein unveiled his general theory of relativity, the most radical reimagining of gravity ever conceived. It was no longer a force in the Newtonian sense, pulling objects together across empty space. Instead, mass and energy warped the very stage upon which reality unfolded. Space and time were revealed as pliable, curving under the influence of matter, as fabric bends beneath a weight. In this grand vision, geometry itself replaced force. And yet, as soon as this theory was released, its implications became unsettling. If space-time could be bent, twisted, stretched, might it not also be folded back upon itself? Could there exist pathways through the cosmos where time itself became circular, where a traveler could journey endlessly through yesterday, today, and tomorrow, repeating them like verses of a cosmic song? The mathematics said yes. In 1949, the Austrian logician Kurt Gödel, already renowned for his incompleteness theorems in mathematics, turned his brilliant mind toward Einstein's equations. What he found was haunting. By considering a universe filled with rotating matter, Gödel discovered a solution in which time was not linear, but looped. In his model, the very fabric of space-time twisted under the influence of cosmic rotation, creating what physicists now call closed time-like curves. A closed time-like curve is a path that bends back into itself, a trajectory in space-time where one could, at least mathematically, return to the very moment from which one began. It is as though time were not a straight corridor, but a hallway curving into a circle, where stepping far enough forward would bring one back to the starting point. Gödel's universe was deeply unsettling. In it, every event could, in principle, be both cause and effect, woven into a circle of self-consistency. There was no privileged now, no forward rush of hours, only an eternal return. To many, it seemed less like a physical reality and more like a nightmare, a cosmos stripped of the very arrow of time that gives life its meaning. Yet Gödel's solution was perfectly valid under Einstein's theory. Nothing in the equations forbade it. The laws of general relativity allowed for time to become a loop. As decades passed, other physicists uncovered similar hints. Wormholes, first described by Einstein and Nathan Rosen in 1935, offered another theoretical doorway to temporal strangeness. These hypothetical tunnels, linking distant points of spacetime, could in principle allow shortcuts not only across space, but across time itself. If one mouth of a wormhole experienced a different passage of time than the other, through acceleration, gravity, or motion, then stepping through might not just move a traveler across light years, but across centuries. One side could open into the distant past, the other into the future. A bridge not only between stars, but between eras. In these scenarios, time ceased to be a one-way street. Instead, it became a labyrinth, full of twists, shortcuts, and potential returns. The very idea was intoxicating, but it was also terrifying. For time loops invite paradox. The most famous is the so-called grandfather paradox. If a traveler could step backward in time, what would prevent them from altering the conditions of their own existence? What if, in some act, they prevented their ancestors' survival, erasing their own presence before it was ever born? Logic buckled under the weight of such possibilities. Physicists sought mathematical escape routes. Some argued that paradoxes might be avoided through consistency conditions, that the universe itself would conspire to prevent contradictions. In this view, any action taken in the past was already woven into the tapestry of history. The traveler could act, but only in ways that sustained the timeline rather than destroying it. The past was malleable only within the limits of self-consistency. Others speculated more radically. Perhaps the act of changing the past would create a new branch of reality, a diverging timeline. In this multiverse of possibilities, each paradox was diffused by splitting worlds. One where the past remained unchanged, another where it diverged. Such ideas, while tantalizing, remain speculative. rooted in quantum theory rather than Einstein's geometry. And still, the mathematics continued to hint that time, under certain conditions, might not be as rigid as human experience suggests. Yet not all physicists were willing to embrace this unsettling possibility. Among the most vocal was Stephen Hawking. In the 1990s, Hawking proposed what he called the chronology protection conjecture. According to this idea, the universe itself conspires to forbid time travel. Whenever closed time-like curves threaten to form, through wormholes, rotating universes, or exotic geometries, quantum effects would intervene, destabilizing the structure and sealing the loophole. In Hawking's words, the laws of physics prevent the appearance of closed time-like curves and so make the universe safe for historians. It was a bold claim, but one rooted not in proof, but in suspicion. A suspicion that nature, however strange, does not permit causality to be shattered. For without causality, the entire structure of science would collapse. Cause and effect, prediction and outcome, the very possibility of knowledge. These depend on time's arrow holding firm. Yet the conjecture has never been proven. It remains an expression of faith in the universe's logical integrity, not a demonstrated law. And so, humanity stands before a deep uncertainty. Are time leaps forbidden, forever relegated to the realm of speculation and fiction? Or do they lurk, hidden within the equations, waiting for some advanced civilization or some freak accident of cosmic geometry to unlock them? The emotional weight of this question is immense. For if time can loop, then history is not a progression but a circle. Lives are not lines but spirals. And causality, the bedrock upon which meaning rests, becomes fragile, a thin veil stretched over a deeper strangeness. Philosophers have long wrestled with this terror. To live in a looped universe is to live in a cosmos without escape, where freedom and novelty vanish, replaced by endless repetition. Yet others see a strange comfort, a vision, where nothing is ever truly lost, where every moment returns eternally renewed. In the silent mathematics of general relativity, both possibilities remain. The equations allow both the arrow and the circle, both flow and return. Which of these realities the cosmos has chosen remains hidden, perhaps forever. For now, human beings move forward, bound to the river of time as they perceive it. But deep within the structure of the universe, the whisper remains. Perhaps the river curves. Perhaps one day it bends back upon itself. And if it does, then the story of existence is not only about beginnings and endings, but about loops, endless, haunting, and eternal. In the long corridors of theoretical physics, time is not always treated as a steadfast companion. Sometimes it is stripped away, dissolved into equations that whisper of a universe where the ticking of clocks is a mere illusion. Here, on the frontiers of thought, physicists dare to imagine what reality looks like when time does not flow at all, or when it flows in ways alien to human experience. General relativity describes a universe woven from the fabric of space-time, bending and warping in the presence of matter and energy. Quantum mechanics, by contrast, governs the microscopic realm with equations that evolve predictably with time. Yet when these two great pillars of science are brought together, they clash. The search for quantum gravity, a theory to unify the large and the small, does not simply ask how gravity and quantum fields interact. It also forces a deeper, more unsettling question. does time itself exist at the most fundamental level? In the 1960s, John Wheeler and Bryce DeWitt wrote down an equation that became the cornerstone of this search, the Wheeler-DeWitt equation. It is unlike any familiar law of physics. There is no time variable within it. No past, no future, not even a present. It is an equation of being, not becoming. A frozen picture of the cosmos, where everything that can exist is encoded timelessly. To some, this absence of time is not a flaw, but a clue. Perhaps at the deepest layer of reality, time is not a river, but an illusion woven from correlations. What humans perceive as moments passing may only be the unfolding of relationships within a static whole. Like frames of a film reel, the universe may contain all events already, and what consciousness experiences as motion is the mind stitching them together into a narrative. And yet, within this timeless picture, other physicists glimpse the possibility of time reversing. For if time is not fundamental, then perhaps its direction is not either. Perhaps the arrow that humans feel, pointing inexorably from birth toward death, from cause to effect, is not universal, but local. A shadow cast by entropy, not by nature itself. Quantum mechanics has long flirted with retrocausality. The equations describing entangled particles do not forbid influences traveling backward in time. Some interpretations even embrace it. In transactional models of quantum theory, every interaction is not just a particle sent forward, but a handshake between waves traveling both into the future and into the past. Reality, in this telling, is a negotiation across time, where outcomes are determined not by a chain of causes pushing forward, but by a network of influences stretching in both directions. This vision unsettles common sense. Brief, it suggests that the future may play as much a role in shaping the present as the past does. It paints a cosmos not of linear progression, but of resonance, where time is less a line and more a web. Among those who have wrestled with this strangeness is Julian Barber, a physicist who has spent decades arguing that time is not real at all. Barber envisions a universe of nows, discrete configurations of the cosmos, each complete in itself. No one now is privileged. They simply exist, side by side, in a grand, timeless landscape he calls Platonia. Brack, what humans call history, is only the mind tracing a path through this landscape, linking one now to another. But Barber has also offered something more concrete, the Janus point model. In this vision, the universe does not expand with a single arrow of time. Instead, it begins in a state of low entropy, and from that point, entropy increases in two opposite directions. Two universes emerge from one origin, each with its own arrow of time. Brack, from the vantage of one, the other runs backwards. From the vantage of the other, ours does. If this is true, then the Big Bang may not have been the beginning of one universe, but the birth of two. Mirror realities unfolding away from a shared cradle, each convinced it alone travels forward, each certain its arrow of time is the only arrow. In the Janus model, humans inhabit one side of the cosmic divergence. On the other, intelligent beings, if they arose, would live in a world where everything familiar is reversed. They would watch stars ignite and burn, galaxies spiral and scatter, lives appear and fade, and to them it would all feel natural. To them it would be forward. Yet from the perspective of this world, their entire history would be running in reverse. Every choice they make, every heartbeat, every breath, unfolding along a timeline inverted from human perception. Such ideas blur the meaning of cause and effect. If both universes are equally real, then what does it mean to say one moment causes another? Perhaps causality itself is not fundamental, but an emergent property of entropy. And perhaps, in some deeper sense, both directions are equally valid. Other physicists turn to the mathematics of quantum gravity and find hints of a similar symmetry. Some versions of loop quantum cosmology suggest that the Big Bang was not a singular beginning, but a bounce. A prior universe collapsed, reaching a minimum volume, then expanded again. If so, then time did not start. It reversed. What is seen as the Big Bang could be, from another perspective, the big crunch of a universe that came before. Across these theories, a common thread emerges. Time may not be what it seems. The arrow, the flow, the certainty of before and after, all may be illusions, stitched into consciousness by thermodynamics and memory. The deeper the mathematics goes, the more fragile these intuitions become. And yet, even as physics strips away the comfort of time, the human heart resists. For everything humans value, love, meaning, legacy, depends on time's passage. Without time, there is no growth, no decay, no story. If time is an illusion, it is one of the most necessary illusions of all. Still, the theories remain. The Wheeler-DeWitt equation, silent and timeless. Retrocausal quantum interpretations, whispering of futures, shaping pasts. The Janus point, with its mirror universes drifting apart from a shared origin. Together, they form a haunting portrait. A cosmos where forward and backward are not absolutes, but choices. Where what is called now may be nothing more than a perspective within a greater whole. Perhaps in the end, the shock of these ideas is not that time might run in both directions. The shock is that direction itself may be a human invention, painted onto a reality that does not care for arrows. A reality that simply is, timeless, eternal, and complete. And in that silence, one is left to wonder. If all moments exist at once, then what does it mean to live a life? If the universe flows both ways, then what does it mean to move forward? And if time itself is an illusion, then perhaps the deepest truth of existence is not the journey, but the stillness in which the journey is already written. In the hidden caverns of modern physics, vast machines hum with the weight of human ambition. Their magnets coil like titanic serpents, their beams race near the speed of light, and deep beneath the surface of the earth, particles collide in an orchestra of sparks. These are the weapons humanity has forged in its quiet war against time. Not a war of conquest, but of comprehension. For to touch the essence of time is to press against the most stubborn veil the universe has ever draped across our vision. At the heart of this quest lie the accelerators, machines that bend and twist matter itself into revelations. Within the tunnels of CERN's Large Hadron Collider, protons whirl through a circular track nearly 27 kilometers long, smashing into one another with energies not seen since the first fraction of a second after the Big Bang. From these collisions emerge fragments, exotic particles that live and die in less than a heartbeat of a heartbeat. Most decay, exactly as expected, following the great ledger of physical law. But a few, like subtle rebels in a rigid kingdom, reveal cracks in the symmetry of nature. It is here that physicists first uncovered what they call CP violation, a tiny imbalance between matter and antimatter, hidden in the decays of strange and beautiful particles. In the 1960s, kaons, particles forged of quarks, were observed to behave in ways that defied the mirror. They refused to decay into their antiparticle counterparts with equal probabilities. Later, in the late 20th and early 21st centuries, B mesons revealed the same defiance. This subtle misstep, a minute tilt in the scales of symmetry, became humanity's first undeniable sign that the arrow of time is not as impartial as mathematics once suggested. For in the language of physics, time reversal symmetry means this, that if the direction of motion for every particle in the universe were inverted, the laws governing their evolution should remain unchanged. But these experiments whispered otherwise. They suggested that nature hides an intrinsic bias, a preference, however faint, for one direction in time over another. This bias, barely perceptible in the laboratory, may be the very reason matter exists at all. For without CP violation, the newborn universe would have crafted matter and antimatter in equal measure, annihilating them in mutual fire, leaving nothing but radiation behind. Instead, something tipped the scales. A breath of asymmetry allowed matter to survive, to cluster into galaxies, to ignite into stars, to cradle planets, and to eventually wonder about itself. And so, the flicker of CP violation inside accelerators is more than an anomaly. It is a relic of cosmic birth, a faint signature that the time we inhabit is not reversible, not entirely symmetric, but forever flowing like a river with one direction. But particle accelerators are not the only watchtowers scanning time's elusive terrain. Cosmology itself, through telescopes that map the heavens, has become a rival soldier in this war. When the Planck Space Observatory measured the faint microwave glow of the cosmos, the radiation left behind from 380,000 years after the Big Bang, it captured not just light, but a frozen fingerprint of entropy. Tiny ripples in that background, imprinted with exquisite precision, reveal the early choreography of matter and energy. Physicists peer into this ancient map, not only to glimpse the infancy of the universe, but to search for the hidden gears of time itself. In the structure of those ripples, in the statistical grain of ancient photons, lies a silent testimony. Entropy has been growing since the beginning. The low entropy state of the early universe, the improbable smoothness of that first cosmic fireball, remains one of science's most profound mysteries. Why was the universe born in such improbable order, allowing the relentless rise of disorder we now call the arrow of time? Every dataset from Planck, every refinement of the cosmic microwave background, is more than astronomy. It is forensic science on the grandest stage, an attempt to reconstruct time's crime scene, to see if somewhere in that primordial light lies the hint of a reversal, a moment when time itself might have flowed differently. Even more audacious are the laboratories that do not look outward, but inward. In the realm of quantum computing, new tools are being forged that may one day simulate the very fabric of time. Quantum systems, delicately balanced, can be engineered to mimic time reversal in miniature. Already, experimentalists have performed simulations where quantum information, scattered like ink in water, is mathematically reversed, recoalescing into its initial order. In 2019, a team of scientists using IBM's quantum computer reported such a demonstration, a controlled reversal of a quantum state, as though a tiny subsystem had been forced to retrace its own history. The experiment did not undo the macroscopic flow of time, nor did it allow signals to travel to the past, but it suggested that within the controlled boundaries of mathematics and computation, time can be manipulated like a variable, rather than endured like a fate. These explorations raise unsettling possibilities. If time reversal can be simulated, if entropy can be momentarily tricked into retreating, then perhaps our conception of inevitability is flawed. Perhaps the arrow of time, so rigid on human scales, is merely an emergent illusion, born of statistics, not of fundamental law. Yet with each step forward, a shadow follows. For every discovery of asymmetry, there arises the haunting question: if time can bend, if it can reverse or fragment or loop upon itself, what becomes of causality? What becomes of the fragile chain of reason and consequence upon which not just science, but human experience depends? Stephen Hawking, wary of paradox, proposed what he called the chronology protection conjecture, a safeguard woven into the fabric of physics to prevent time from tearing itself apart. Though his words were directed at wormholes and closed time-like curves, they echo even in the halls of quantum computing and particle physics. Perhaps there are unseen laws, deeper than those yet written, that forbid the most dangerous manipulations of time. Perhaps the universe guards its own chronology as fiercely as a temple guards its secrets. Still, the war continues. Each particle decay studied at CERN, each photon captured from the edge of the observable universe, each qubit entangled and reversed in delicate choreography. These are the battlefronts of an invisible conflict. A conflict not fought with weapons, but with patience, mathematics, and the quiet hope that the veil will one day lift. Yet the deeper the search goes, the more the mystery resists. For even as accelerators reveal asymmetry, even as the cosmos whispers entropy secrets, even as simulations mock the arrow of time, the human mind cannot escape a chilling realization. It may be that time is not an absolute to be conquered, but a perspective to be endured. That every tool, every experiment, is not defeating time, but merely learning to dance within its boundaries. And so, beneath the earth in particle tunnels, across the heavens through telescopes, and within the fragile architecture of quantum machines, science continues its war with time. Not to break it, not to undo it, but to understand why it flows at all. For perhaps the greatest terror is not that time cannot be reversed. The greatest terror is that it never existed in the way we thought. That it is but a story told by entropy, a tale whispered by the universe to make sense of itself. And that when the tale ends, when the last particle decays and the last photon fades, there will be no forward, no backward, no past, and no future. Only silence. In the equations that govern the universe, time appears as a ghostly symmetry. Newton's mechanics, Maxwell's electrodynamics, Einstein's relativity, and even the quantum formalism, all can be written in such a way that if the arrow of time were flipped, the mathematics would remain intact. A movie of the cosmos, run backward, would still be a valid solution to the same fundamental laws. Yet reality disagrees. The stars do not collapse back into hydrogen clouds. The ashes of a burned tree do not reassemble into wood. A glass shattered on stone does not leap upward, restoring itself into perfection. In every corner of daily life, time carries with it an undeniable sense of direction, an asymmetry that the equations themselves seem unwilling to confess. This contradiction between mathematics that permits reversal and a cosmos that insists on forward motion is one of the deepest fractures at the heart of physics. The arrow of time, in its most accepted form, is entropy, the relentless statistical drift toward disorder. In a closed system, the probability of chaos overwhelms the probability of order, driving the universe from low entropy beginnings to high entropy futures. This is the second law of thermodynamics, and it has never been seen to fail. But entropy is not an explanation, it is a description. It tells us how the arrow manifests, but not why it should exist in the first place. If the fundamental equations are reversible, why did the cosmos begin in such an improbably low entropy state? Why did the Big Bang not emerge already drowned in chaos? Why was there order enough for galaxies to form, for stars to ignite, for life to arise and contemplate the mystery? Here lies the unresolved paradox. For some physicists, entropy itself is the only true arrow, the single law that whispers of irreversibility. Yet others sense something deeper, something hidden beneath probability. They point toward the possibility that time's asymmetry is not a universal law at all, but a boundary condition, an initial choice, as if the universe was wound like a clock in its first instant, setting the cascade of moments into motion. Still, the mathematics resists confinement. In the Wheeler-DeWitt equation, which merges general relativity with quantum mechanics in a timeless description, there is no parameter for before or after. The universe exists as a frozen block of possibility, where every event, past, present, and future, simply is. In this view, the flow of time is not a feature of the cosmos, but a projection of human perception, a way the brain orders experience into a narrative of continuity. If this is true, then the arrow of time may be less a law of nature and more a cognitive construct born from consciousness itself. The mind remembers the past, but not the future. Neurons fire in cascades that depend on previous states, not on what lies ahead. Memory is asymmetric. Causality, as lived, is asymmetric. Perhaps the universe does not march forward at all. Perhaps only the mind does. Yet even in this daring speculation, physics remains haunted. For if consciousness gives rise to temporal flow, then entropy still awaits explanation. Disorder increases whether or not there is an observer to witness it. Stars still burn their fuel. Black holes still evaporate. The cosmos still grows old. The arrow of time is written into the bones of reality, not merely into the mind. The threat to physics lies here, in this dissonance. Equations whisper symmetry. Reality demands direction. Between them yawns an abyss. Some suggest that hidden laws remain undiscovered, laws that tip the balance and carve time into forwardness. Others believe that what we call forward is an emergent illusion, a collective hallucination woven by the unfolding of probability from improbable beginnings. In the cold silence of the cosmos, these questions echo without answer. The paradox remains unresolved. If time symmetry truly holds, why does the universe resist it? If entropy is the arrow, why was the bow drawn in such perfect order? And if consciousness is the craftsman of temporal flow, then what is the true nature of reality, when no mind is present to watch the moments fall? The threat to physics is not destruction, but incompleteness. For as long as time flows only forward in experience, while equations allow reversal, the human story of the universe remains unfinished. Perhaps the future will reveal that the arrow is not an arrow at all, but a shadow, an artifact of beginnings, destined to fade when the universe grows quiet. Or perhaps it is eternal, carved deeper than law, deeper than mathematics, into the very essence of being. Until then, the arrow pierces onward. Each tick of each clock, each flicker of each star, each thought that passes in the fleeting spark of a mind, together they affirm what the equations deny, that time, whatever it is, does not stand still. In the fragile weave of existence, time feels absolute. It carries every life from birth to death, every star from ignition to collapse, every universe from creation to dissolution. Its arrow seems unyielding, pointing forever forward. Yet hidden in the mathematics of physics, there lies no law that forbids its reversal. The possibility remains, quiet, unsettling, that the cosmos could just as easily unravel itself as it weaves itself forward. To imagine such a world is to step into a mirror, a universe that does not march toward disorder, but retreats toward symmetry, toward order, toward the beginning itself. In such a reality, death would not follow birth, it would precede it. Bodies would rise from graves, bones would knit into flesh, lungs would fill with air, and a final breath would not be an ending, but the first act of living. Children would return to the womb, and existence would fold into silence before ever being born. But the terror lies deeper, for in this inverted universe, memory itself would flow in reverse. The human mind, bound by neural patterns shaped by entropy, would not recall what has been. It would instead remember what is yet to come. Dreams would be prophecies, not recollections. Decisions would be guided not by past lessons, but by futures already etched. The present would feel like a constant echo of destinies already lived. The meaning of free will would dissolve, for choice would no longer be a forward creation, but a backward inevitability. Every act would feel scripted by what has already occurred at the other end of time. Entropy, the quiet architect of decay, would no longer scatter order into dust. It would gather dust into symmetry. Shattered glass would leap from the floor into a seamless vessel. Smoke would curl backward into the flame. Galaxies, now spiraling into gravitational chaos, would instead contract into perfect spirals like cosmic clocks ticking back to zero. The heat death of the universe, that final silence where all gradients vanish, would not be an ending, but a beginning. Out of thermal equilibrium, structures would reassemble, stars would reignite, and time would flow inexorably toward an ordered birth. In such a cosmos, the very concept of progress would vanish. To live forward in a backward-flowing time would feel alien, for every moment would bring not novelty, but familiarity. The future would already be known, because it would already have happened. Free will, the essence of human identity, would fracture into paradox. What is a choice if the outcome is already remembered? What is individuality if consciousness is nothing more than a mirror held up to a timeline unfolding in reverse? And yet, some physicists suggest that the distinction between forward and backward may itself be illusory. Julian Barbour, in his Timeless Models of the Universe, suggests that time may not exist as a flowing river at all, but only as a structure of possible arrangements, the timeless nows of reality. If this is true, then the flow of time, whether forward or backward, may be nothing more than a trick of perception. Humanity might not inhabit a universe moving in one direction, but rather one static architecture, where all moments coexist, where existence is a gallery of states frozen in eternal stillness. In such a framework, living in backward time is no stranger than living in forward time. It is simply a matter of where awareness is anchored. Consciousness may crawl along one branch of this timeless structure, giving the illusion of motion, while other branches unfold in opposite directions. What feels like life from birth to death could be mirrored by another consciousness living death to birth. Both equally real, both equally complete. The philosophical consequences are staggering. If time's arrow can reverse, then morality itself shifts. To harm someone in forward time is to cause pain in the future. But in reversed time, would that same act heal instead? Would cruelty undo itself and kindness unravel? What meaning does good or evil hold in a cosmos where consequences march backward? The cosmos itself whispers no preference. The equations of quantum mechanics, of relativity, of fundamental particles carry no prejudice for direction. They permit time to move forward, or back, or not at all. The asymmetry humanity clings to is carved not into mathematics, but into entropy, into the fragile unfolding of disorder. It is not that time cannot flow backward, it is that it almost never does. But imagination asks, what if? What if existence is already mirrored, and somewhere beyond perception lies a world where entropy retreats, where futures are remembered, where beginnings lie in endings? Perhaps what is called now is only one half of a cosmic Janus face, two universes leaning back to back, flowing away from a single point of origin, one into disorder, the other into order. And if this is true, then what humanity calls life may already be doubled, its reflection moving silently, invisibly, in reverse. To contemplate backward time is to feel the fragility of reality itself. For if time is not absolute, then neither is death, nor memory, nor choice. What appears to be the inevitable march of moments may be only a narrow path in a timeless labyrinth, a single thread among countless others. And somewhere, perhaps, another version of existence already walks the opposite road, retracing every step, moving not toward tomorrow, but toward yesterday, where every ending is a beginning, and every beginning waits patiently at the end. Time has always been a mirror, showing not only the universe but the human mind gazing back at it. Across continents and centuries, long before laboratories and particle colliders, people looked into the sky and saw not emptiness, but eternity. What they saw became myths, philosophies, questions that would echo across ages, shaping the way humanity thought about existence itself. In the cradle of Western philosophy, the Greeks asked what time truly was. Parmenides, the poet-philosopher of the 5th century BCE, declared that change itself was illusion. To him, reality was a frozen, eternal block where past and future coexisted, and what mortals called time was only a trick of perception. Heraclitus, in contrast, saw everything as flux. No man ever steps in the same river twice. To him, time was the eternal fire, consuming and creating, the heartbeat of a universe in motion. Two visions, standing opposed like twin reflections, one seeing permanence, the other seeing ceaseless change. Both were incomplete, yet both planted seeds that physics would rediscover millennia later. Eastward, another tapestry was being woven. In the Vedic hymns and Hindu cosmologies of India, time was not linear but cyclical. The universe was said to breathe in great ages, yugas and kalpas, cycles of creation, destruction, and rebirth. In this vision, time was not an arrow, but a wheel turning endlessly. Stars and worlds lived and died like sparks in an infinite fire, only to return again. In Buddhist thought, the cycle of samsara, the endless turning of birth, death, and rebirth, captured another truth, that time was bound with consciousness itself. To awaken was to step outside the cycle, into the timeless state of nirvana. The East spoke not of clocks or arrows, but of circles, spirals, and endless returns. In the 4th century, St. Augustine, writing in the twilight of Rome, struggled with a paradox still unsolved today. "What is time?" he asked. "If no one asks me, I know. If I wish to explain it, I know not." For Augustine, time was inseparable from the soul. The past existed only in memory, the future only in expectation, the present in fleeting awareness. The cosmos might unfold in days and ages, but time, in its deepest sense, was the measure of a mind stretching across them. Even now, neuroscience confirms the fragility of temporal perception. Memories stitched together, predictions woven ahead. Our sense of a now, no more than a fragile construction of neuromachinery. Augustine's insight lives, echoing in modern science, like a voice carried across 1,600 years. Centuries later, Albert Einstein shattered the old absolutes. In the geometry of spacetime, he showed past, present, and future are not universal. They are relative, depending on one's motion, one's gravity, one's frame of reference. Time dilates, slows, bends, yet never breaks. When his lifelong friend Michele Besso died in 1955, Einstein wrote in mourning, "For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion." To him, the universe was not a river carrying beings downstream. It was a vast landscape, already existing in totality, where what we call now is merely the place where consciousness happens to stand. The block universe, Einstein's inheritance, echoed Parmenides across 2,000 years. But Einstein's vision carried a wound. If time is illusion, then what becomes of choice, of change, of becoming? If every moment is equally real, then life itself seems trapped inside a sculpture already carved. Yet entropy, the great law of disorder, tells another story, that universes evolve, stars burn, and glass shatters irreversibly. Between Einstein's timeless block and the second law's relentless arrow, a contradiction remains. Philosophers and physicists alike have tried to bridge it. Martin Heidegger, the German thinker of the 20th century, argued that human existence, our being, was inseparable from temporality. To exist is to be stretched between a past we inherit and a future we anticipate. Time is not a background. It is the horizon of meaning itself. In this, Heidegger unknowingly echoed Augustine, and perhaps the Buddhists, that time is not merely out there in the cosmos, but in here, woven into consciousness. And yet cosmology paints its own strange reflection. The Big Bang suggests a beginning, a singular moment from which time itself may have emerged. But quantum theories hint that before the bang, the distinction between before and after may not even apply. Julian Barbour, a contemporary physicist and philosopher, suggests that time may not exist at all. Instead, reality may be a collection of nows, individual configurations of the universe, like still frames in an infinite archive. Our perception of flowing time, he proposes, may be no more than the linking of these frames in memory. Here, ancient paradoxes breathe again. Augustine's fleeting present, Buddhist timelessness, Parmenides' eternal reality. If time is an illusion, then humanity stands in a peculiar position, trapped inside a dream of succession, while the universe itself rests beyond it. But if time is real, then why does it move only one way, carrying us endlessly toward decay? The echoes of philosophy do not fade. They return, refracted through modern science. The Greek river, the Hindu cycle, Augustine's present, Einstein's block, they are not relics, but lenses through which physics itself continues to peer. Each captures something that equations alone cannot fully reveal. The strangeness of living inside a cosmos whose most basic dimension defies understanding. Perhaps the truest lesson of these echoes is humility. That time is not only a problem of physics, but of human existence. That equations may measure its dilation, but not its meaning. That entropy may reveal its arrow, but not its essence. As long as humanity wonders, the ancient voices will whisper still. What is time? A river, a wheel, a prison, a dream, or something beyond words altogether. And as the cosmos unfolds, whether by arrow, by cycle, or by timeless stillness, the question remains, not solved, not silenced, but echoing across centuries. Time, like a river, has always been imagined as flowing towards some distant ocean, a place where its restless current must eventually surrender. But what is that ocean? Is it silence, stillness, a dissolution into featureless emptiness? Or is the end of time a return to its source, a circle closing in eternal recurrence? The human mind cannot resist seeking the horizon of all horizons, the fate of the cosmos itself. Physicists and philosophers alike call it the ultimate question. How does the story of everything conclude? In this pursuit, cosmology becomes less a science of measurement and more a science of prophecy, guided not by omens, but by equations traced in the language of gravity, entropy, and quantum fields. One possibility lies in the bleakest of visions, the heat death of the universe. This fate emerges from the second law of thermodynamics, the principle that entropy, the measure of disorder, tends always to increase. Over billions upon billions of years, stars will exhaust their fuel. Galaxies, now bright islands of light, will fall into darkness. White dwarfs will cool to black husks. Neutron stars and black holes will remain as sentinels. But even they cannot resist eternity. Hawking radiation, the faint quantum whisper from the edge of black holes, promises that even these giants will evaporate over unimaginable spans of time. When the last one dissolves, nothing will remain but thin gas, photons stretched into oblivion, and particles too sparse to ever interact. The universe would not end in fire or in ice, but in stillness, an eternal twilight where time still ticks, but nothing of consequence ever happens again. In this heat death, the arrow of time does not reverse. It continues, endlessly, but with no events left to mark its passage. Time becomes indistinguishable from timelessness. Yet the cosmos may harbor a different destiny, one hidden in the curvature of space-time itself. If the universe contains enough matter, gravity may one day halt its expansion and pull everything back together. Galaxies would drift closer, stars would collide, and cosmic structures would collapse into a final implosion, the Big Crunch. In such a vision, the end mirrors the beginning. The fire that once expanded might contract back into singularity. And here, speculation dares to go further. If time is linked to expansion, then could its arrow reverse as the universe collapses? What would it mean if the ticking of entropy ran backward, if disorder gave way to order? To an observer inside such a universe, the collapse might not feel like an ending at all, but like a beginning played in reverse, where death unravels into birth, where ashes gather into fire, where galaxies shrink into a point that is once again a seed. This dream of reversal invites an audacious thought. Could the Big Crunch give rise to another Big Bang? A new universe, not separate from ours, but a rebirth of the same. If so, then perhaps every life, every star, every thought has been lived and will be lived again, caught in the eternal heartbeat of creation and collapse. But modern measurements cast doubt on this destiny. The cosmos is not slowing in its expansion. It is accelerating, driven by the mysterious pressure of dark energy. If this acceleration continues unchecked, a different fate looms. Not a crunch, but a cold and lonely infinity. Galaxies will drift so far apart that their light can no longer cross the gulfs between them. The night sky will empty. Civilizations, if any endure, will see only their local stars, never knowing the vast cosmos that once existed beyond. This is the fate cosmologists call the Big Freeze, the quiet march toward entropy's kingdom. Yet even here, mystery stirs. If dark energy is not constant, but grows stronger with time, then acceleration could tear space itself apart. Galaxies, stars, planets, even atoms would be shredded in what some theorists name the Big Rip. Time would end not in stillness, but in violence. The fabric of reality split at its seams. And then there are speculations more daring still, born from the strange mathematics of inflationary cosmology. Inflation, the rapid expansion that likely ignited our universe, may not have been a singular event. It may be eternal, spawning bubble universes in an endless froth of creation. In such a multiverse, some universes may follow our arrow of time, while others may flow in the opposite direction. To their inhabitants, time would feel as natural as it does here, yet from our perspective, their cosmos would seem reversed. Entropy there would decrease, not increase. Galaxies would assemble from dust. Stars would ignite from ash. Perhaps even beings would walk backward into the womb. These universes, if they exist, remind us of how parochial our sense of time may be. What feels absolute may only be local. Time's arrow may be a feature of this bubble, not of all bubbles. And so the greatest paradox emerges. Could the end of everything be indistinguishable from its beginning? When cosmologists study the equations of general relativity, they find a symmetry, an echo of circularity. The singularity that marked the Big Bang is, in mathematical essence, not so different from the singularity that could end it all. Beginning and end are both horizons where physics falters, where equations lose their meaning, where time itself dissolves. If these horizons are in truth the same, then perhaps creation and annihilation are two faces of one coin. Perhaps the universe is less a line from birth to death, and more a loop, a breath, an eternal pulse where the beginning of the end and the end of the beginning are one. Such speculation forces reflection upon existence itself. If the cosmos is destined for stillness, then meaning may lie not in permanence, but in transience, the fleeting sparks of order in a sea of growing chaos. If the universe will collapse and rise again, then perhaps life is woven into a cycle far grander than birth and death, a rhythm of return. If eternal inflation spawns countless worlds, then ours is but one note in an infinite symphony, unique yet repeated in endless variations. And if the end is the same as the beginning, then perhaps the true mystery is not where the universe goes, but why there is something rather than nothing, why time has a river to flow at all. N.P. Cosmology edges toward these horizons with humility. Telescopes measure the faint afterglow of the Big Bang. Satellites track the expansion of space. Equations seek to unify quantum uncertainty with the curvature of spacetime. But for all its power, science reaches a precipice where knowledge blurs into wonder. At that edge, the universe whispers a final enigma. The end is not yet written, for the end may be the beginning, and the beginning may be the end. And so the river of time flows on, toward stillness, toward collapse, toward branching eternities. No one knows which destiny awaits, but in the search for the end, humanity discovers a mirror of its own longing, to know whether life is a fragile accident, destined for silence, or part of a story that never truly ends. Sob. The question lingers like an echo, carried across the cosmic sea. If time could reverse, where would it take existence? Would it spiral back into the past, retracing the footsteps of galaxies, stars, and human lives? Or would the backward flow of time open a door not to history, but to something altogether alien, beyond even imagination? In the great cathedral of physics, equations whisper of reversibility. They tell us that nothing prevents the film of reality from running backward, that the dance of particles is as valid in reverse as it is in progression. Yet the lived world resists such symmetry. Glass shatters, but never leaps whole from the ground. Smoke disperses, but does not gather itself back into flame. The arrow of time, sharp and unwavering, cuts forward. But suppose it could bend. Suppose entropy, that grand law of disorder, could be coaxed into retreat. The story of existence would not simply rewind like an old tape. It would not be the past visited again. It would be a world unfamiliar, ordered in ways the forward-flowing mind cannot conceive. A universe where backward time reigns would not show corpses rising from graves, nor shattered vases restoring themselves from the floor. For the human brain and the memory it houses are themselves constructs bound to forward entropy. In a backward realm, minds would not recall what was, but what will be. Memories would point toward what we call the future, even as their bodies marched into what we call the past. Death would not precede birth as a grotesque inversion of sequence. Instead, existence would weave a different fabric of causality, in which the very concepts of before and after are rearranged into something unrecognizable. Physicists have long wrestled with this paradox. In the laws of Newton and Maxwell, of Schrödinger and Dirac, time has no preference. These equations do not decree a forward march. They allow both directions with equal grace. The asymmetry arises only when entropy, the measure of disorder, asserts its sovereignty. It is this swelling tide of entropy that makes broken eggs irreversible, that gives heat its one-way descent into balance. But if entropy itself could reverse, then the cosmos would no longer dissolve into disorder. It would crystallize into ever greater structure. Galaxies would not drift apart into darkness, but gather into luminous whirls of perfection. Stars would not exhaust their fuel, but ignite from ashes, climbing into brilliance from their own remains. This is no mere fantasy. Certain cosmological models allow for it. In the scenario of a big crunch, where gravity eventually overwhelms expansion, the universe would contract. As space collapses, so too might entropy. Some theorists suggest that at that moment, time's arrow could reverse. What we see as the end would merge seamlessly with a new beginning. The universe would not perish, but be reborn in reverse. Yet from within, no observer would know the inversion had occurred. For in that reverse domain, memory itself would point the other way. Consciousness would flow along with the altered arrow, convinced always that time is moving forward, even when by another frame it is moving back. Backward time, then, may not lead anywhere at all. It may not guide existence to a retraced past. It may only reveal that direction itself is illusion, that forward and backward are labels imposed by a mind too small to glimpse the whole. In Einstein's relativity, space-time is a block. Every event, every heartbeat, every flicker of a star exists together timelessly. Past, present, and future are slices carved by perception, not divisions inherent to reality. For us believing physicists, Einstein once wrote, the distinction between past, present, and future is only a stubbornly persistent illusion. If that is so, then backward time is not a path, but a perspective. To imagine it is to turn the head and look upon eternity from another angle. In the grand block of space-time, there is no river flowing, neither forward nor back. There is only the eternal tapestry, woven all at once. To speak of backward time leading anywhere may be as mistaken as asking where north leads when one already stands at the pole. It leads not to another place, but to a deeper recognition that time's arrows are human inventions, and reality is not bound to them. Still, the speculation lingers like a haunting. If backward time were real, if entropy could decline, what would become of human freedom? Would choice still exist in a world where causes follow effects? Or would free will dissolve, revealed as nothing more than the illusion of a mind swept along a track already laid? Some philosophers argue that free will is an illusion even in forward time. For in a block universe, all actions already exist, fixed within space-time's geometry. To them, backward time only underscores the point that freedom is perception, not fact. And yet, there is another possibility. Perhaps free will is not destroyed by timelessness, but revealed in it. Perhaps the human sense of agency arises not from altering the future, but from inhabiting a perspective within the block. Like a traveler, wandering a landscape that already exists, the will is not the power to carve mountains or rivers into being, but the experience of choosing which path to tread. In backward time, as in forward, the walker still walks. the journey still feels like choice, even if the land has always been there. Thus the question becomes not, where does backward time lead? But what does backward time reveal? It reveals that beginnings and endings may be illusions of vantage, that death and birth may be only edges drawn around a cycle far larger, that universes could bloom in both directions from a single origin, one with entropy rising, another with entropy falling, each believing itself to be the only forward flow. In this vision, backward time is not an aberration, but a partner, two mirrors facing each other across eternity, reflecting creation without end. For cosmologists exploring eternal inflation, this is no idle dream. In such models, universes bud like foam on an infinite sea. Some may expand with entropy increasing, others may unfurl with entropy decreasing. Each would house beings convinced of their forward arrow, unable to imagine that beyond their horizon lies a cosmos flowing the other way. What is backward to one universe is forward to another. Reality, in its totality, holds both, indifferent to human preference. And so the tension reaches its climax. Backward time does not lead to the past, nor even to a different future. It leads only to a deeper recognition that forward and backward dissolve into timelessness, that the question itself is misphrased. Where does backward time lead? It leads nowhere, for there is nowhere to lead within eternity. Time's directions are shadows cast on the wall of a timeless chamber. To reverse them is not to walk a new path, but to turn and see the chamber itself. In the silence of that chamber lies the final revelation. Time is not a river, not an arrow, not even a dimension to be traversed. It is a story told by the universe to itself, a narrative woven from entropy's growth. Forward, backward, chapters, not the book. And when the story is seen whole, when the pages are laid flat, the beginning and the end meet. Backward time does not lead into history, nor into prophecy. It leads into the realization that history and prophecy are one, reflections on the same eternal mirror. Thus the chapter closes, not with an answer, but with an unveiling. The cosmos holds within it both arrows, both flows, both illusions. To ask where backward time leads is to step into the mystery itself, to glimpse a truth too vast for human measure, that all directions, all moments, all worlds are facets of a single timeless reality. And perhaps that is the ultimate destination, not the past, not another universe, but the timeless stillness where forward and backward dissolve, and eternity itself becomes the only truth. The human mind drifts like a fragile vessel upon an unseen current. For centuries, that current has been called time. It is spoken of as a river, flowing endlessly forward, carrying birth into maturity, maturity into decline, and decline into death. Yet the more closely science peers into its depths, the more illusory this current becomes. Perhaps it does not flow at all. Perhaps the river is an illusion conjured by perception, and the vessel has never moved. Physics paints time not as a stream, but as a dimension, a vast landscape in which every event, from the first trembling of atoms to the last fading of stars, already exists. In this view, moments are not carried away. They are simply arranged like pages in a book or frames upon a reel of film. The past has not vanished. The future has not yet emerged. They are all there, waiting, fixed within the geometry of space-time. Then memory does not capture what has been lost. Instead, memory is a thread that ties a mind to one coordinate on the cosmic map, giving the illusion of movement. Identity itself may be nothing more than a pattern in the tapestry, lit briefly by the spark of awareness. And yet, humans feel time. They feel its urgency. They feel its weight. Every heartbeat is measured against it. Every choice feels like it is carved into its flow. Every goodbye carries the ache of irreversibility. But physics whispers otherwise. The arrow of time, the sense that events move only in one direction, may not be fundamental. It may be an artifact of entropy, a shadow of disorder increasing, not a law of the cosmos. If entropy were reversed, then time too would seem reversed. Stars might grow brighter as they consumed chaos. Ashes might gather themselves into burning logs. The dead might rise, live, and return to the womb. But such visions are not simply rewound tapes of existence. They are glimpses into structures beyond ordinary comprehension. For if forward and backward are equally possible, then perhaps neither exists. Perhaps time, as it is felt, is an invention of consciousness, a scaffolding the mind builds to navigate a reality that is, in truth, timeless. Einstein once wrote that for those who understand relativity, the distinction between past, present, and future is only a stubbornly persistent illusion. His words echo with unsettling calm. If the present is not privileged, if the future already is, then what does it mean to live, to choose, to love? Humanity has long struggled with this paradox. Augustine of Hippo, gazing into the mystery of existence, confessed, "What is time? If no one asks me, I know. If I wish to explain, I know not." Centuries later, modern science finds itself repeating his bewilderment, dressed in equations instead of prayers. Perhaps memory and anticipation are the twin illusions that construct the sense of self. Memory gathers what is called the past. Anticipation projects what is called the future. Between them, the mind stitches a fragile thread, calling it I. But if the fabric of the universe is already complete, then this thread does not run through it. It only hovers upon it. The I may be a mirage suspended in stillness. This reflection does not diminish the wonder of existence. Instead, it deepens it. For if every moment already exists, then every smile, every tear, every breath is eternal. The laughter of a child does not vanish into silence. It is written permanently in spacetime. The final heartbeat of a life is not swallowed by oblivion. It remains, frozen, alongside the first heartbeat that ever was. Even the cosmos itself, its birth and fire, its slow unfolding into galaxies, and its final dissolution into silence, may not be a story with beginning and end. It may be a sculpture, already complete, extending beyond comprehension. A monument of being, within which humanity is but a flicker of consciousness. And so the mystery circles back. If time is not a river, but a landscape, then the search for beginnings and endings dissolves into illusion. The universe does not truly begin, nor does it truly end. It simply is, always. For the human heart, this truth is unsettling. To live feels like to move, to strive, to hope. To love feels like to lean toward a future not yet born. But if there is no future, no past, only an eternal now, then love itself may be more profound than ever imagined. It is not fleeting. It is not lost. It is woven forever into the silent fabric of reality. And here lies the final reflection. Backward or forward, yesterday or tomorrow, these may all be illusions cast by perception. What remains, untouched, is the eternal now, a presence beyond decay, a truth beyond all beginnings and ends. Perhaps this is the silent answer to the riddle of time. Not that it flows, but that it never has. Not that it ends, but that it never began. And so, when humanity gazes into the mystery of time, into the abyss of entropy, the riddles of physics, the cycles of philosophy, it meets only a mirror. In that mirror is reflected a question it cannot escape. What is life if time does not move? The mystery does not yield. It does not bend. It does not open. But in its silence, there is beauty. In its unanswerable depth, there is wonder. And in that wonder, perhaps, is the truest meaning of existence. For if time can flow backward, it leads not to yesterday. If it can flow forward, it leads not to tomorrow. It leads only to this, the eternal now, the silent truth beyond all beginnings and all ends.